In this video, we'll discuss the concept of related rates. So in previous videos, we talked about implicit differentiation, where you can find the derivative of an expression involving one variable, but with respect to a different variable. So as a just quick example, if we have an expression like y squared, right? And I want the derivative with respect to x. Well, this sort of implies that those variables are connected. Like if y and x are totally connected, then the rate of change would be, say, 0, basically, because this is saying when the x variable is changing, how does this expression change? Well, if they're unrelated, then this would be 0 in that case, because they're not connected. Changing x doesn't affect y, so 0. So when we ask this and it's assumed to be meaningful, well, that means that they are connected, that y equals some function of x. We just don't know what it is. Okay? So basically, when we have y squared as the input for this derivative operation, we have a function of a function. This is g of x squared, right? Y squared equals g of x in parentheses squared. We have an inside function and we have an outside function. So we need to use the chain rule, right? So if you were to apply the chain rule to this, looking at that, you'd say, oh, well, my outside function is 2. So dx of y squared, or rather I should say it's 2 times something. This is dx of g of x squared, right? So this is going to be 2 times the inside function times the derivative with respect to x of that inside function. Okay, because we have the power rule and then the chain rule. Okay, power rule and chain rule are both at work. Okay, well, the inside function will just sit here, 2 times g of x, and the inside function will sit here, derivative of g of x. Okay, now 2 times g of x, well, g of x is y, remember? So this is just 2 times y. Times, well, since we don't know a formula for g of x, we're just using it symbolically, it's what y is, well, this is dy dx, whatever that derivative might be. We don't have access to it right now because I don't have a formula for g of x. So this is what's going on under the hood. When I look at this guy, I go, oh, the outside function is the exponent 2. I'm squaring something. So the derivative is going to be 2 times the inside function, and then times the derivative of that inside function. Okay. Now that's just a survey of implicit differentiation. Now, how does this relate to related rates? In related rates, instead of having derivatives with respect to x, we're going to have derivatives with respect to t, time. So like if I had a little display error there, I wonder how that happened. Oh well, let's not worry about it. If I have something like dt of y squared, y is changing over time, well, this is the same idea. This is 2y times dy dt. Whatever that happens to be, that's what it is. Until I have access to that as a formula or as a number, I just have to leave it the way it is. In a related rates problem, typically you'll be given, well, y is changing at this rate, 2 units per second or 2 units per day or whatever it is. Now, let's say I had an equation that described something tangible. So I'm going to use something that's, let me get another page here. I'm going to use something that's, current events, something that's relevant now. Let's say that the number of employees, let's say at HEB, right, who are going to get sick from customers being sick. Someone with coronavirus, goes to this. They don't know they have it yet, right? They're asymptomatic. They go in to buy some toilet paper, right? They're hoping to get some, and they, ask an employee, "Hey, are you guys restocking today or tomorrow morning?" And then they buy something else because there's no toilet paper. They buy some, I don't know, ramen or something, and they go and they pay for it, right? And assuming that we don't have these social distancing practices in place, which are useful, they're having an effect. But supposing we didn't, right? This is like a month ago or 2 months ago. There's no, say 2 months. There's no social distancing. Someone who has this virus, they don't know they have it. Well, let's say the number of employees, let's say across all all HEBs, or it could even be one large HEB, pick like the one Days of Olive, right? So let's say the number of employees who become sick at that store as a result of just the general public coming in, whoever it might be. Let's say that it's something like, I don't know, 0.1% of the number of customers squared. Okay. Let's say there's 2 points of contact. The customer comes in, they ask an employee a question, and then of course when they go to check out, they have to interact with the cashier. So there's 2 points of contact. I'm not an epidemiologist. Let's just pretend this makes sense. I'm just making up an example, right? So let's say the number of employees who get ill, who become ill, let's say that is in proportion to the square of the number of customers that day. So number of customers each day, right? And let's say become ill each day. This is both like per day, right? Well, what I can say is, well, what would happen if fewer people go to HEB? Let's say on a day-to-day basis, fewer of them are going. So let's say at this particular store, there's, let's say, I don't know, 5,000 customers per day. And that's probably not even a big HEB. That's probably a little HEB. Well, if the number of customers is 5,000, then the number of employees who become sick at some point, after interacting with that person, maybe this number is too large, maybe it's exaggerated. Let's add a couple more zeros in there. Let's say 0.000, let's say 0.1. Let's do like that, right? An extra zero or 2 extra zeros. So then E is going to be, for that particular day, 0.00001 times 5,000 squared, right? That's 5 million times that's going to be 50, okay? Oops, sorry, struggling with the interface here. I hit the wrong button. 50. So that day, 50, and this doesn't have to be coronavirus, this could be anything, and again, I'm making this up, so don't take the numbers too seriously. So 50 employees will become ill from having worked that day, right? Based on having 5,000 customers that day. Well, what if the number of customers goes down by, let's say, 1,000 from one day to the next? C goes down. Let's say 100, by 100 customers, by 100 each day. Okay. Well, that could be represented as dc dt, the rate of change with respect to time, the derivative of the number of customers as a function of time. That's going to be negative 100. It's going down by 100 each day, and we'll say that t is in days. Okay, well, if that happens, how will that affect the number of employees who become ill each day? Well, we can use implicit differentiation to find that. What I really want to do is take this equation that relates the number of employees who become ill to the number of customers who are seen that day, and I want to turn that into an equation about the rate of change, the rate of change, or the rate at which employees become ill and the rate at which customers are coming to the store, right? Again, assuming no safety measures. So I'm going to apply what I like to call a time derivative to this equation. So I'm going to copy the equation down here. Okay, so E equals 0.00001 c squared. I'm going to apply the derivative with respect to time to both sides. Okay, so on the left, I'm finding, well, what is the derivative? What is the rate of change in the number of employees who become ill with respect to time? Well, that's dE dt. The number of employees who become ill as a function of time is some formula. I don't know what it is. I don't have a formula for it. So I'll represent this as dE dt. Okay? And same thing on the right. This is slightly more complicated. I have to apply the derivative as a function of time to 0.00001 c squared. So I'm going to use the power rule and the chain rule. So this will be, come on, struggling with the interface again. this will be the power roll 0.00002, right? The 2 multiplies against the 1. C to the first power times, using the chain rule, the derivative of the inside function, which is C. Again, I don't have a formula for C as a function of time, but it's implied to be one. dc dt. Okay, so if dc dt is negative 100, as I said, and C is 5,000, how will that affect the number of employees who become ill? Well, then if dc dt, there's other notation for this, but we'll get to that in a later video. We don't need to get bogged down with notation. If dc dt is negative 100, then de dt, well, that will be 0.00002 times, C was 5,000 for that particular day, times the rate of change for that day. So the next day will be 4,900 customers instead. If we multiply this together, we're going to get, I believe, 10, I think. Do I have a calculator handy just to be sure? I think I do. Here we go. So let me turn the light on. Sorry about that. Okay, so 0.00002 times 5,000 times negative 100, and I get negative 10. Of course, negative. What that represents is the following day, 10 fewer sick employees. So if you just reduce the number of customers coming in by just 100, from 5,000 down to 4,900, you'll go from 50 employees who become ill down to 40, down by 10. So this is what related rates will do for you. When you have an equation that connects two quantities, number of customers, number of employees, that kind of thing, and you know how one or the other of them behaves over time, you can then decide, well, how does the other one behave over time by finding the derivative with respect to time on both sides of the equation and plugging in the numbers that you know. So this is a relatively basic example, and hopefully you can see the importance of this kind of analysis, calculating these kinds of things. So in the next few videos, we'll do more examples like this, but a little bit more complicated as far as the calculus component.